This paper is with Fazlidin Shermatov, Stefano Bianchini. You may know Faz. Faz is an EPOC student, and he did most of the work. So unfortunately, he's not yet here. He told me he will arrive in 15 minutes, so let's hope he's going to be around because he will answer questions. I won't. Third reasons why I'm uncomfortable, because in the last 25 years I've used PowerPoint. Unfortunately, when you have young co-authors, they use this very sophisticated word processing, some online tool, and of course, the product is a PDF, and it will not work for sure because I have my green, nice, exactly, the computer never works, slides, and instead I have to use the PDF, no dynamic or statics. Okay, that's life. So, David, I don't know, sorry? And then fourth, David is bothering me at the start of my presentation. And now there is a echo. Okay, I keep on bullshitting till when it's done. So again, seriously, this is a part of the dissertation of Fazli. Fazli has worked with Stefano Bianchini in Strasbourg for his master dissertation last year, and then he started the PhD. And this idea of the paper came about in December, January, when we were in Torino eating at a restaurant. And we thought, whoa, that's a good idea. Why not we? And yes. And this is my first presentation of this paper, so I'll try to do my best. Faz has already presented some attempt. And we actually sent it out to a journal, a top journal, to be rejected as usual. Those of you that will continue in the PhD, you will learn that our sport is being rejected, okay? And you have to learn to have a thick skin and say that's life. This paper has been already rejected by science. Okay, now we move to nature and we'll see if we go through. I doubt. Huh? You send it, you get rejected, and then you go down the ladder of journals. I keep on talking, meanwhile, I don't know what he's doing. I almost stopped to say crazy things, and I would like to start with the presentation, but he's not there yet. Can I? No, I keep on bullshitting. Okay, so the paper is on, actually no, the idea came at the restaurant because master dissertation of Fazli was on top 500 high-performance computers, and he discussed and did the data analyze that. And then we were trying, it would be nice to actually do on all high-performing computers. So the idea was originally to understand the diffusion of high-performing computers in science. Okay? What it is a high-performance computer is a tool that helps scientific discovery. Of course, this doesn't work in this one. How do you go down with PDF? Okay, like this. Motivation, I can finally start. I'm trying to convince you that what you will listen in the next 45 minutes from now is interesting, okay? That are the three phases of the 2004 Nobel Prize in Chemistry. Do you know them, by the way? Can you tell us who they are? AlphaFold, does it tell you something? Oh, come on, guys. I mean, it's the most important step in biotechnology. It's one of the most important steps in artificial intelligence use. These are the two leading figures on AlphaFold, DeepMind, Google, okay, development of. AlphaFold, prediction of proteins, okay? So we had the understanding of the human genome about 25 years ago, and then we thought, wow, it's the new age for biotechnological drugs. It didn't turn out like that because proteins are much more important. And then a private company, two leading scientists of the private company, wins with a scientist of a university a Nobel Prize for chemistry because of the way in which proteins are folding and for the development of a tool, AlphaFold, that predicts unfolding of proteins. So all this is to tell you, this is a university industry typical interaction. So top private company researcher in artificial intelligence related topics, top biochemistry researcher, received the Nobel Prize, and they could have not done that if there was no artificial intelligence and if there was no the computing power behind this. So very large computer, high performance computing. Okay, so similar story. By the way, do you know who's Hinton? Nobel Prize are important people, you know. Hinton is the father of AI. Some of you are doing word analysis, are using LLM. Actually, all of you use LLM now. Okay, without Hinton, there would be no LLM. ChatGPT would not be there. And he actually is a computer scientist from Toronto, but then he won the Nobel Prize for Physics because his tool were used again in physics. So that was the 2024 Chemistry and Physics Nobel Prize. So two traditional scientific fields, traditional in which Europe is still important nowadays, but the reason for winning was actually the computing and artificial intelligence capability behind the simulation and the prediction model done in those two areas. So that is science, why it's important. And then there is another important discussion out there that is the diminishing return. Okay? If you know something about growth modeling, not post-Keynesian, Schumpeterian, the basic idea is recombinant. Recombinant what? Recombinant knowledge. You recombine knowledge, more knowledge you produce, more you can recombine, more you can recombine, more you can grow. Okay? Knowledge, what it is, innovation, blah, blah, blah. I don't want to do that class. But we believe till recently that actually more science produced, more science will be produced. So increasing return fundamentally rather than decreasing return. Came out a couple of papers. I'm not too convinced about them, but they got a lot of success and a lot of attention that we are facing decreasing return in most recent year. By the way, those two papers, a lot of economic research is usually based on US data because the data are there, because that's the dominant country, especially in economics, and so those are the data. Clearly, science has become extremely capital intensive. Don't think of the mathematician solving a problem, think actually of a large laboratory with 10, 15 people, and with heavy computing capacity. Okay? So more resources to advance research. That is true. You need more resources. If you need more capital, capital after a bit is decreasing, and you have decreasing in science. It might be. Okay? Another story that I could tell you instead is based on the Kuhnian idea of philosophy of science, of paradigms, of burst and low period. Science is not linear. Okay? There are suddenly big jumps forward in what science discovers, and then there are more stationary period. So what these two papers showed may be simply stationary period. This paper, I'm going to present you in the next 40 minutes, tries to argue that actually we maybe are entering in a new phase of burst in science, and this new phase of burst in science is based on availability of new tools. Okay? Remember the birth itself of science. One of the seminal work was actually Galileo. I'm Italian, it's not for that reason, but it's the telescope. Okay? The telescope opened the way of verifying a series of theories that back then were discussed. Okay? The world is round or is flat? The church was saying the sun or the earth, okay? And then with the telescope you started to do observation, physical observation, and you could test those theories and provide proof of those theories. So it's the typical example, but then think about in the 80s, the digital microscope, okay? The biotechnological revolution is also based on that specific instrument that allows you to go to the nano dimension. Ciao. So we are around in this discussion. So instruments are important. They're extremely expensive. So there might be decreasing return in science. On the other side, science is discontinuous, is non-linear, goes in S shape, goes in slow growth and then sudden growth, and so on and so forth. So we enter in this debate with empirical analysis. This is the Kuhn, Rosenberg. Rosenberg is an historian of science and technology, showed this very nice paper on the digital microscope. Increasingly so, I don't know, but definitely since Galileo onwards, resource infrastructure, telescope, or a big accelerator, or a high-performance computer are foundational for scientific progress, okay? Are the needed instrument to go and test theories. Think about CERN and the accelerator. You know the accelerator in CERN is a big, huge kilometers ring. That is an instrument, okay? It's an instrument to test theories. That instrument has costed billions. Okay, so resources dictate speed and trajectory of research. So more resources, more output. More resources, better output if you want. What we actually are interested in is not only more publications. Of course, there has been an explosion of publications in the last 20 or 30 years. There are a lot more more PhDs, there are a lot more postdoc, and there are a lot more scientists. And that meant a lot more publications, okay? But what we care is actually the elite of these publications. So those publications that are novel, a quantum of novelty compared to before. And in my field of research in the last 10 years, we have spent quite some time to try to come up with indicators of novelty. With not much success, I have to say. I mean, every 2 or 3 months comes out a new paper with a new indicator. What are they really measuring? I don't know. So I'm using a few indicators too on novelty to try to capture these. So the idea of more resources, more novelty, more contribution, but pay attention to how these measures are done because they actually measure different things, most likely. So again, supercomputers, revolutionary scientific instrument. Okay, let me try to explain you, and David told me that you will go. You know what is this? It's actually somewhere here, on the first floor. It's in the museum here, yeah? I was there last year and I took the picture because I was so excited to see it. Okay, so this is a supercomputer. Let me take you back to the 50s. In the 1950s were called mainframe, and they were big like this room, but they were not supercomputer. They were computer to do fast calculations, okay, for administration. These are supercomputers because are scientific instruments developed to do very specific type of calculation related to simulation. By the way, Fazli is here. He's going to answer the questions finally. Specific calculation related to simulation and testing. So there are 2 different types of machines. They're not just big computers, but they are, as I was saying, scientific instrument. Cray 1 is, you see, that's the Cray 2. The Cray 1 was 1976, was the first, and Cray was the inventor, by the way. So it's typical, is a scientist that is developing a tool to do a specific experiment. He needed a very special calculator, and that was the Cray 1. Okay, a lot of this is happening. You sometimes think about science as very different from technology. No, 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 no. Actually, a lot of science depends on technology. You need a specific technology to test something. And again, supercomputers are an example of this path. Going beyond the theoretical concept, they were used in astronomy, in material science, in earth science. So it's not something new of last 10 or 15 years. It's something that was there, but in the paper we argue that something has happened. So from this machine that is Cray 2, we move to the machine that we now have that are supercomputer HPC. So you know Moore's law? Do you know Moore's law? Can you tell us what is Moore's law? Yeah.
He's mostly known for so-called Maslow's law. So, I mixed him up with Moore, but Maslow is the guy who does the test if there is an artificial intelligence. So you go into interaction with the subject with the computer.
No. This is Moore's law. This is very simple. Doubling of computing power are roughly every 18 months. Okay? Everything you see in front of you, those computers, used to be a big room. So Moore's, okay, given silicon, given the miniaturization of the chip, computing power has kept on increasing. This law, he was an IBM manager, by the way, he was nothing else than someone managing the production of chips in IBM. This law is, we are getting to the nano level in microchips, okay? So it's becoming problematic. On the other side, there is growth in high-performance computers, okay? So because they are assembling more and specifically they started to use GPUs and move to parallelism instead of single computing. So there has been a significant restructuring of the architecture of HPCs that enable to keep on increasing computing capacity. The Moore's law is physical, okay? After a certain dimension, or we go to a complete new technology, or there will be no increase of computing capacity any longer, except if you change architecture and you go to parallelism. So it's been exploding, expanding, especially in the period we analyze, along growing scientific demands. Okay. Artificial intelligence, you know more. You might know about this paper. This paper is the first paper in 2012 that applies fundamentally deep learning to a competition that is ImageNet to solve image recognition. So before 2012, what we now is known as deep learning and neural network were actually not considered the dominant form of artificial intelligence, but this paper using GPU accelerated ways, so the technology again is the use of GPU that allows those AI models based on neural network to be run in an efficient way, won the competition of image recognition. That is the first most important discontinuity in artificial intelligence. We move from one type of artificial intelligence towards deep learning. Second, very important moment, transformer. How many of you know transformer? 1, 2, 3, 4, okay? Maybe someone of my class do know. That is Google again. They develop a specific architecture. They actually, 2017, didn't know what to do with it. I mean, they thought it was useful, but they release it openly, okay? So they didn't patent, they didn't take a copyright. It was there, and that transformer architecture fundamentally is a specific architecture to do neural network structures, powered the LLM revolution, okay? And as was released open, was used by everyone that wanted to use it. Finally, most recently, due to the AI revolution, there is increased computing demand. Almost every 6 months, this was 2022, but that's quite constant, computational demand for AI model is doubling. So we see a lot of demand for computing driven by the development in most advanced artificial intelligence. Okay, so what is this? I will come back to the end in the discussion. This gives you an inequality index, and is an inequality on 56 countries. Again, Fazli is the father of this data. In his PhD has collected supercomputers. What it shows there, and then we will discuss, FLOP is the measure of speed of high-performing computers. Then we can discuss if FLOP is the right measure or not, and in the case of artificial intelligence is not, but it's the most used measure to quantify the computing capacity is telling you that in this period there has been a huge increase in inequality in the power, computing power at the country level. Okay? So there is a lot of demand, but the supply of computing power is getting more and more unequal, more and more concentrated. So we will discuss in the conclusion that this is problematic from the point of view of science, because if that computing capacity is becoming a necessary condition for scientific development, being more and more unequally distributed means that fewer and fewer countries can have access to the frontier of knowledge, and that is fundamentally what we are trying to argue in this paper. So artificial intelligence, what it is artificial intelligence? But we don't know, or there are a lot of different theoretical papers discussing it. Accelerated discovery across discipline is a general purpose technology, is a general method of invention, algorithmic manager, large technical system, God knows. I don't particularly care, fundamentally. But all these papers are telling us that is something in this new configuration, deep learning, the evolution of deep learning, and the most recent evolution of LLM through transformer, that is impacting technology and science, has become a fundamental tool of scientific discovery. You are using artificial intelligence. You are using to write your dissertation, to do your research. You are using to write the code of econometrics. You are using it to write Python. Okay, it's impacting you, student, and it's impacting us, researchers. So it's has become a tool, part of our daily life. So what we are interested in this paper then, is there a synergetic effect? Is there a coevolution? The two technology arrive to a certain stage of development. For me, technology are the HPC, so the high-performing computing, and artificial intelligence. Artificial intelligence is a technology, a technoscience, fundamentally. So they both interact, and they might have a more than linear effect on scientific production. So what is the combined effect? Pay attention to the word effect. There is no causal identification in this paper. It's correlational analysis. Next 6 months, maybe we will move to causal. So effect here is very, very much between quotes. It's correlation, but still. Is science most recent scientific frontier development, our most recent scientific frontier development correlated to HPC AI? Very simple paper, very simple question. We try to answer to that. So the issue now is how you measure. Okay, you are going to write a dissertation in the next 6 months, and the most important thing I'm telling always to students is the outcome. Okay, how do you measure what you want to explain? Is the start, we were at lunch in a restaurant, and we thought, oh, we can measure that thing like that. Okay. So if you are not clear on how to measure your outcome, you don't build this thesis structure. Okay? So measurement has to go hands in hands with your theoretical development, your research question development, and so on and so forth. So we want to measure HPC. We are interested in the diffusion of the technology within science. We want to know which scientists have used our performing computers. The idea is, let's look at the acknowledgements. Okay? Usually in scientific papers, less so in papers in humanities, but always in natural science and quite often, most often in social sciences, you have an acknowledgement. I acknowledge my array, I acknowledge the founding, I acknowledge the comments of my colleagues, and I acknowledge actually the use of the HPC of the university. In a lot of cases, the high-performing computer is of the university, and the researcher got access. We are using the one of Torino for free. We have been using the one of Strasbourg for free, and therefore you acknowledge the use. So we use that. Does it make sense? We are measuring. I'm always suggesting to talk to people. So do some interviews, talk to the people that are managing this facility, and I had contacts in Torino, so I knew the director of the supercomputer of Torino, and we went to talk with him and a few of his colleagues to know exactly how power was allocated, they were paying money, they were not, so to validate a bit our idea of acknowledgement. Once we did it through the interview, however, I have to convince you that what we do is actually that proxy, that measure, is actually quite good proxy, quite good measure. So we do a validation phase. We obtain the complete list of all researchers from the University of Strasbourg, a list of the researchers that have used the high-performing computer in Strasbourg. 111 is more recent, smaller, the one of Torino. Fazli, not Aldo, has developed an LLM, analyzing a subsample of full-text paper. So we look at all the paper of these researchers. There were 10,000, something like that. Of course, I have used an LLM in a few of my papers. I haven't used, an HPC in only one of my papers, this paper. But in these years, I have produced 5 papers. So out of the 10,000 papers, only a subset of those have used the HPC. So we have to find a way to identify that. So Fazli has developed an LLM that has read the full text of the paper, so that reading the full text, if as use an HPC, is similar to use econometrics. I use this tool, okay? I use this molecule, I use this compound. So I've used the HPC, and maybe you find it in the text. You should find it into the text of the paper, because it's methodology. You have to explain your methodology. So the LLM goes and identifies that about 60 to 70% of the paper that were identified by the LLM reading the text as having used an HPC also acknowledged it in the acknowledgements. Okay? So I'm telling you, using the acknowledgement, we can't read millions of papers, of course, because it will take a couple of years. Papers, texts are not fully available. In this case, they are only available on Scopus or for a subsample. There are a lot of limitations in using publications because of the access to publication. So we use an easier proxy, but we validated it through a systematic analysis of the full text. Of course, you can tell me, yeah, but it's an LLM. LLM are stupid, so you made mistakes. So Fazli read a few papers. So that's the human check, that's Fazli check, and the random extraction of the sample, and indeed confirm that all those that were classified by the LLM as positive, they were actually used. There was the sentence, there was the paragraph in which there was the use of. Nowadays, LLM, here what have you used? Gemini, no? Gemini 2. This is done by Gemini 2, is pretty good in classifying, in reading text and extracting and classifying. So they are becoming really reliable, but still pay attention, a bit of human feedbacks, especially for the prompting. Okay, the first prompt didn't work so well. It did a bit of check on human reading the paper, then did a second prompt, and the second prompt worked much better. So that interaction phase is always required. Okay, a few numbers. These are 280,000 papers that acknowledge HPC, high-performing computer, supercomputer. We use a few keywords. They were used there. I told you they started in 75, okay, by very little, and then they exploded in the most recent period. From 0.05% in 2000 to 0.8, about 1% in 2004. So exponential growth of the number of papers that they have used an HPC in their scientific research, and this is a lower bound estimation, because when we check in Torino and in Strasbourg, it was about 30% more. So this is a lower bound estimation of the real use of HPC in science. How is the field distribution? Of course, you expect what chemistry and physics and astronomy is what I show you in the 2 Nobel Prize laureate. Earth, chemical engineering, material science, multidisciplinary are simply nature and science, okay? Energy, big energy model, and so on and so forth. Then computer, engineering. But okay, you see here medicine, social sciences, economics. Those are the annual compounded growth rate. So for example, in our area, 27% compounded growth growth rate on every year, on the periods considered. So they are, of course, concentrated in the traditional field that they were using HPCs from the start, but a lot of new discipline in, okay? Second part, we are interested in artificial intelligence. How do we measure artificial intelligence? Again, we use publications. There has been a long discussion how to proxy, how to get the publications that are in artificial intelligence. There are long lists, 360, 370 keywords. We did not trust them. So again, Fazli, not me, did some robustness check on the keywords. We decided for a list of 203 keywords, and we extracted 5.7 million papers from the corpus of Scopus. So the complete Scopus in this period accounts for 66 million publications, documents, okay? So about 5, 6 are papers that in the abstract keywords or title have one or more keywords that are within this list of the 203 keywords of. The top 10 keywords are convolutional network, deep learning, I don't remember them, they are on the paper, are the traditional word associated to deep learnings. And they account for the large majority of the publication. And then there are a lot of other keys that are less frequent, but they are. That's okay, it's a large database. Can we codify 5 million to an LLM? No, it takes too long, okay? Again, pay attention to LLM because we have to do calculation of time. Here we are running on a HPC, all of these, not on a laptop. So even running on a HPC, we could not use all that corpus to try to test better because we don't trust the keyword. It's incomplete, the keyword, okay? It's just a proxy for. What we did, our focus of analysis is the HPC, our performing computers, okay? So we have 280,000 or something like that papers. How many do we have? 280, yes. So we downloaded the full text for 110,000 papers of the sample that acknowledge the HPC. And then we run with Gemma 2, 3, 2, 7b, z, yx, God knows what Fazli did, an LLM, so that could analyze the full text. So we asked the LLM, and in the appendix of the paper you have all the prompt, so that you can read in detail what we want, what the prompt is. I learned something about doing LLM. Do as much as possible a very, very, very long and clear prompt only once. Okay? That's the more precision you have in that prompt, and that's that phase of trial and error in which you have to understand what is the proper prompt. Once you have understood the proper prompt, you go, and then you ask scores usually. You don't ask a yes or no. You ask a score, and then you ask a reason for giving that score. So that then on a random extractions of the reasons for that score, then you can try to do a second round of validation. Anyhow, we did this process, and then we crossed the keywords with an LLM for that sample of paper, 93% of agreement. So it's pretty good. So the keywords actually were quite good. Fundamentally, they converge. However, doing an LLM, we could ask them, and this is the interesting part of the paper, I think is the most important conclusion and most original part. Did they use it to advance, to develop IE, or did they use IE for use, so to do something else in a scientific field? So it's the idea of, is this a new IE model, so there is advancement in computer science, fundamentally field, or is something else? So it's a use of pre-existent algorithm. So the question is, you have IE developers and IE users. Fundamentally is what we try to do. Are we able to classify papers in that way? And again, we did this work, and we succeeded, and now I will show you the data. So these are the data on artificial intelligence, from less than 5% in 2000. Remember, 2012 was CFAR identification of images. 2017 was Google release open of transformator, and you see again quite an exponential growth. 15% of total scientific output is in 2024 is somehow connected to artificial intelligence. Okay, already this number is impressive, I think. It means that 50% of all publications indexed in Scopus are somehow linked to a very specific technology that is called artificial intelligence. So if you want one message to take it home, artificial intelligence is heavily impacting science, of course, especially in most recent years. Okay, that is 2024. Pay attention, environmental science, economics, econometrics, finance, important growth rate. So this is not within the science, because scientific impact can be within that scientific field or across a scientific field. This is a tool, is an instrument, is a technology that is impacting outside computer science, is impacting all sciences. Okay, so remember, we are interested in understanding if there is a coevolution, if understanding if there is a synergetic effect. Then we look at the share of IE paper. No, wait, this is HP within IE. Yes, IE within HP. We look at the 280,000, so the HPC paper, and we look at the share of this paper with IE. How much is the share of paper that acknowledge an high-performance computer that have used IE tools? Okay, we start from around 3-4%, 4-5%, and we go up to about to 16.4%. Okay. So we see a bit more than in general science. So IE has grown significantly in combination with HPC. The other percentage is much lower. So what it tells you, about 1% of all IE paper use HPC. But remember, IE paper are 5-6 million. Has grown also that one, much less. That means that there is, if you want, microcomputer. I mean, you run, till this year, last year I did a paper using IE, but not using the HPC. That was the common tool. So on a normal laptop now you can use simple IE model that are contributing to your scientific research. So here the point is, the two technologies are used, and especially artificial intelligence is used in HPC. This graph shows you what we were testing. I think we are the first one to have tried to measure this. This is the increase of development, and this is, of use, and this is development. Fundamentally, it's not general IE that is growing, but is actually the use of IE. So I take an algorithm already, Gemini 2, whatever, and I use it for my own analysis. I'm not developing a new LLM. So the big growth in our sample of papers, this is, remember, the subsample of high-performance computers. So there are scientists in various disciplines that are taking some IE algorithms and they are applying for their own model mainly. There is a bit of growth also in development, but not so much. So much of the growth of the IE use is actually IE use. Interestingly enough, now look at the fields compared to all those that we were looking before. This is again a subsample of HPC for which we have the full text. There is no statistical difference, right? No, there is no statistical difference compared to the total population, and then we look for development of use, and you see much more heterogeneity up there, and not the traditional field. Look at medicine, how important it has become, okay? So because a lot of medical research now on big number, precision medicine, is run on HPC using IE models. So that would be the example of this kind of. Okay, till now the story has been, first we measure HPC, okay? HPC technology has become important. Second, we measure IE. IE technology has become important. Third, the two are interacting. I see more frequently the use of both technologies together. Okay, so next question is, do they have an impact? Okay, impact again between quotes. Causal identification is not here. Now it's descriptive statistics. So what do? What we always do in bibliometric, as I told you, lots of paper, only very few gets a lot of citations. Some, probably 20 to 30% of paper published, even in top journals, are never cited. 0 citations, okay? 0 citation is incredible. It means that an article published on American Economic Review has not been useful to anyone, okay? Because it's never been cited, okay? That's crucial. Fundamentally, I'm telling you that a lot of my time is just bullshit. I'm writing things that no one is reading, okay? So I don't want to measure that. I want to measure, give you satisfaction, yes. I want to measure the top 1%, the highly cited, the really those that are contributing a lot. Then we can enter on, this is bibliometric, it's really impact, it's really quality. On the top 1%, I would not dare to challenge them. They're really, really top scientists, okay? But, okay, don't, in this case, is extreme. So I really take extreme, elite science, the best science that is there, okay? 7 field, 27 field, again, a lot of work of Fazli to classify this field, ask everything to Fazli, 7 years. We got 347,000 publications. We stratified them across field. In different fields, there are different top 1%. We want to be representative in those fields. We ended up with 9% were classified in IE-related and 1.2% in HPC. So what is telling you that within the sample of the highly cited, there are a lot of papers that are in artificial intelligence, a bit less than the total share. Remember that was around 15%, but this is the stock of last 7 years. And there is a bit more of HPC, because the top level of HPC was 0.8 in the last year, and here is 1.2%. So first message, they are represented a bit more, and then I'll show you true field. And then we use the indicator I told you not to use, but to use with care. So we pick one. In the next version of the paper, we will use another one. We pick this one because it's a recent paper published on the RES, Review of Economic and Statistics, and the data are publicly available with the DOI, so it was quite easy for us to link the DOI. DOI is the publication identifier, to use the DOI to link and create this. So we look at new words, new phrases, new combinations, so it's a textual analysis in the abstract and in the title to find something that is new, okay? The typical example I'm giving, because I studied that field a lot of time ago, is combinatorial chemistry. Okay, these two words together did not exist, were put in a journal in 1992, okay? So it's coevolutionary network. 20 years ago, the two words coevolutionary network did not exist together. So do you understand what novelty measure is? An attempt to use words to capture new idea in science. The problem that there are various ways of doing that. There are various ways of, but okay, we use one. We can discuss then later on if it's useful or not. We look at novelty in the top 1% field. Why we are trying to combine two measure proxies for frontier research. I want highly cited paper that are novel, because there might be highly cited paper, but they are not so novel, okay? Novelty, to give you an example, in terms of new word, is 5% of the sample. Okay, it's very, very small. 5% of all the papers had, in the period to consider, introduce a new word. Okay, so that are novel. So we look at only these and only for those 7 years. Some descriptive. This is the field variance. I started at 2. Oh gosh, I need to move. okay, 1 is 1%. If it is above 1, it means that those papers in that area are getting more than the average. Okay? This is IE, this is HPC, this is the combination. Systematically, across field, is the combination of the two that gets more often in the top 1%. Okay? So when papers are using both IE and HPC, then they have a higher probability, around 2.5%, to end up in the top 1% category. Novelty, here we have all papers, the 380,000, then HPC, IE and HPC, HPC and IE. Again, if you look at the Bordeaux, is most often on top. So descriptively, I'm telling you that those papers that have used both the two instruments, artificial intelligence and HPC, the two technologies, tend to end up more often, tend to become more often highly cited papers, okay? Tend to be more often in the category of novel papers. Next step, of course, we run a small econometrics. This is a simple probit, could have run a logit. We are interested in the interaction effect, so when the two are active, we estimate IE and HPC. We have controls, two sets of controls. Okay? We are interested, as I said, in the interaction, in the synergetic effect. So what do we control? Prior citations. Stars, highly cited, will have more probability of being highly cited in the future, will have more probability of being novel. Okay? We need to take into account the fact that science is very cumulative. Paper level, the bigger the sire, the bigger the probability of being cited and novel. International collaboration. Shimago journal ranking is the quality of the journal. So try to get some measure of the quality of the team and of the journal, because we expect to be correlated with citation and novelty. And then institution, we know that the parking order in science counts. If you get a degree from Harvard or from UTC or from Torino, it's kind of different. Okay, and then type of affiliation. Okay, and that is in science too. Okay, so we control for a series of indicators that could explain our dependent variable, but are not there. We use, of course, fixed effect, 27 fields, affiliation country because of differences in founding, publication year because of different trend in publication. Control for heterogeneity. Okay, the more fixed effect you can, the better it is, so that you compare simple things. The sample again is the top 1%, 7 years. We cluster at the journal level the error, because we know that there are journal level effects, and so we try to cluster there. Again, this is a correlation analysis, not a causal analysis. We don't have a strong identification. We are working in the next 6 months to see if we can instrument. I don't have any longer time for the statistics, so let me jump to results. And these are the results, and fundamentally we are interested in this variable. So HPC DAM is positively correlated with new words. We are explaining novelty, okay? So the more, positive correlation for IE, a positive correlation for the interactions. Okay, once you go and look at the probability, this is what you get. Controlling for all the factors we control, those papers that have used both artificial intelligence and HPC technologies have a higher probability of being in a novel paper. Okay? IE and HPC, there is not such a major difference. These two compare all papers, there is a difference. So really what it matters is the combination of the two in terms of novelty. So although see if the two of them individually are more than the full population, and only when they are together that you get this bust in novelty. Novelty, again, if you remember my starting of this work, has been science is growing, decreasing return, or in burst. Okay? And so if there is a lot of novelty in a certain period, it means that science is non-linear. Now I need to convince you that the results are robust, and we do a lot of robustness check. Here we use other novelty measures, so new phrase, new word combination, new phrase combination, semantic distance, top semantic distance, so the top 25%, this is the most extreme one, and fundamentally the results are robust. So we calculate again probability, in most cases they are. In the case, pay attention to indicator of new phrases and combination of new phrases and combination of new words, the share of new is quite high and therefore has lower power of disentangling defect. While the two that are more extreme, semantic distance and words, the results are robust. We exclude journal rank so that we can run on the full sample, because journal rank exists only for 190,000 observations, so we want to be sure that reducing the sample to 190,000 does not have an impact, nothing changes. We have papers, look at descriptive. We have papers with 7,900 authors, okay? This is nuclear physics. Of course, those are really weird paper, so we want to exclude those, and we exclude those and nothing is changing. We exclude about 5,000 paper. There is a paper with 400,000 citation in 20 years. No, in 7 years, because it's the stock. Yeah, it's the same. No, 400,000, this is citation. I think it's the stock of citation in 7 years. Anyhow, some papers are really super cited. Prior citation, no, it's prior, it's 10 years. Is the stock of prior citation. So there is at least one author that in the previous 10 years got 400,000 citations, to give you the scale of what these people are. Science is very, very, very skewed. So we take out those, still the results are identical. Okay? Next step will be to try to instrument and try to move a bit more towards a causal identification. Okay, let me close now, going back to the starting discussion. Why is this relevant? Okay, this might be relevant in terms of inequality in science, okay, on the distribution of scientific capacity. So we create a measure of computing capacity. Again, Fazli did. This was his master thesis. And then we downloaded the full corpus of 63 million paper of Scopus, and we calculate inequality measure on that corpus. What we do, we use the generalized entropy index. We use the generalized entropy index because it's particularly sensitive to the tail, so to where we are interested in inequality. It is what is mean, log deviation, blah, 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 fundamentally zero perfect equality, and then increases. And then I'll give you the example and explain. So this is the graph you already seen in terms of computing capacity. So the first result is, as I already told you, computing capacity has become more and more concentrated in a subset of countries, United States and China. Okay, Europe is there, yeah, Germany, Finland, Italy, France, but look at the size. So there is a concentration, and of course here there are 56 other countries, global south, that they are there. They enter, right? They have some. There are a lot of countries that enter with a supercomputer, but then in terms of flop, that is very different, okay? So are much more powerful, much more parallel HPC that have been created, especially in those countries. Second evidence, these are the publication. This is the overall trend of inequality in publication. By the way, about 4 means 55 times the typical country, okay? So it's quite high level of concentration of inequality, but it's decreasing. And then look at artificial intelligence and look at HPC. There has been a huge phase of catching up. So especially artificial intelligence is above the average science in terms of inequality. Okay? Where is concentrated? China, United States. Okay? Then you have India. Here size matter, because this is the total number of papers. You have Europe somewhere there, and you have the other country. This morning, we did this graph because, of course, as I started, there are a lot of publications. So big countries, India, China, has a lot of output. But what we are interested is actually top citations. When you look at top citation, actually here it's missing still the country. I hope that they were there, but they're not. There is the artificial intelligence and average. So what in the last 7 years, at the end, in the top 1%, inequality in artificial intelligence is as equal than in science. So fundamentally it's telling you the most recent science of top quality is highly unequal. What is interesting of this graph is actually the HPC stay there quite constant. And it's about 1 compared to about 2. Okay? This, of course, is only those countries that are in the top 1%. So the level of inequality is much lower. In the previous graph, look, here we are 3.5. Okay? There we are about 2. Okay? Because in the first one, there are all countries. There is Zimbabwe, I saw this morning. Okay, so you have whatever country that is published. In this one is only top 1%, and so in the top 1%, you have a subsample of countries. But the important message here, that in the top 1%, HPC is less unequal than artificial intelligence and then general science. And then I link this result to the conclusions. So this is what I already repeated. Let me jump to the summarize and conclusion. Paper using both IE and HPC do scientific research tend to have higher impact and greater novelty compared to other paper categories. Seems that we find some evidence of a new burst in science. Of course, this has to be re-estimated in 10 years to see if our prediction was good. We are concerned about scientific stratification, because if these two tools have become extremely important in scientific discovery, we saw an increase inequality in HPC, an increase in inequality in IE, even more in IE in general than HPC. And this is the final comment. If I want to become a policy advisor, you are following an economic policy master to the ministry, both in Europe and in the global south, would I advise to invest in new IE models? DeepSeek, maybe it was an hype, this DeepSeek so little costly. Or would I advise to heavily invest in hardware, in computing capacity? Probably I would advise in computing capacity, because it's still less unequal. Players are still there. The leading countries are not so far away. Of course, we keep on reading that Google, Facebook, Meta have huge investment in computing capacity to run their models, but the inequality is lower. So if there is a catching up possible, Europe has to catch up. It's global south. There is slightly different positioning, but it's China and the US that are up there and are running this business nowadays. It's probably in hardware capacity, in supercomputer capacity rather than. So in training people in sciences that are able to use development versus use versus development, so they're able to use the IE tools. There is no need of developing them. They're too far away to catch up in development. But they're able to use those tools to do other science on the computing capacity of those HPCs. Maybe open discussion. Now we are the discussants. Thank you very much for attending.